in order to study binding energy in order to form a nucleus or to break up a nucleus, we should probably understand the idea of mass energy equivalence here. Because by understanding a mass energy equivalence, only we are able to understand where does the energy comes from. Okay, when we have energy released, where does the energy comes from? When we say we use energy to break up a nucleus, where does the energy comes from? So mass energy equivalence will be able to answer that question. Okay, so the idea is all objects have mass, so have a corresponding intrinsic energy when they are stationary. Okay, so in the usual case, when we study about physics from semester 1 until now, the kind of energy we talk about is always usually kinetic energy or potential energy, or sometimes we talk about internal energy when we are talking about heat, those kind of discussion. So potential energy is the energy that is stored due to the location of the object. Kinetic energy is the energy that is possessed due to the motion of the object. So if you are at a certain position, it might cause you to have a certain potential energy. If you're moving at a certain speed, you're able to have certain kinetic energy. If you are at a certain temperature, you have a certain amount of internal energy. So those kind of energy are associated with how you place the object, how you move the object, or what is the temperature of the object. Okay, but now we are going to talk about another kind of energy which doesn't require any kind of requirement, like where do you place it or how do you move it or how hot is it. You don't need to look at those kind of things. When I'm going to talk about a kind of energy which is there as long as you are an object, you will be having the energy. Okay, why do you have the energy? It's because you have mass. As long as you have mass, you will have some amount of energy. And that kind of intrinsic properties of energy, right, we call it as rest mass energy. Okay, when they are at rest, their mass will contribute to a certain amount of energy. So we call this as rest mass energy. Okay, so all objects have mass, have a corresponding intrinsic energy when they are stationary. So this is not related to how you move it, not related to how you place it, not related to how hot is it. Just by being an object, just by being something with mass, you have a certain amount of energy. Okay, so in the rest frame of an object, don't worry too much about rest frame. Just think of it as when an object is at rest. Okay, your V and your P are equals to 0. V is your speed, P is your momentum. So your speed and momentum are both 0. Okay, the mass on energy, okay, sorry, probably some editing mistake. The mass and energy are equivalent and they differ only by c squared. Okay, so when we are talking about an object that is at rest, when they are not moving or when their momentum is equal to 0, for that kind of case, how much energy do we have just by being something with mass? The amount of energy that we have just by being something can be described by this equation over here. So if you are if you're an object of a certain mass, how much energy do you possess just by being an object can be determined by taking the mass of the object multiplied by c squared, and you're able to calculate this value called the rest mass energy. Okay, but this energy here is not something that you can simply use anytime you want. Okay, kinetic energy, if you want to increase it, you just push it faster. If you talk about potential energy, you want to use it, you drop it from higher ground to lower ground, then you are able to use that potential energy. But when we're talking about this rest mass energy, right, it is an energy that you have just by being something with mass. But this energy here is not something that you can just immediately extract by pushing it or by placing it at other position or by heating it up. You can extract this energy. No, okay, this energy is there because you have mass. So if you really want to tap into this energy, you have to do something to the mass. You have to reduce the mass or you have to increase the mass, which is something quite advanced. Okay, if you remember when we talk about physics, right, there's something called conservation of mass. So mass, right, will not be easily destroyed or formed. Okay, so when we do chemical equation, you have to make sure that the mass remain constant for the reactant and the product, right? So mass is not something that you can easily destroy, or mass is not something that you can easily create. Okay, so even though this rest mass energy, right, is a very large amount of energy, but it's not something that you can easily tap into. Okay, it's not something like exothermic reaction, endothermic reaction, or like heating up or something like that you can extract energy. No, this is a totally different story. It's an energy that you have just by being something with mass. But because the mass, your mass is constant, so the energy you have, right, you cannot just simply extract it. Okay, so later when we study about binding energy, we will understand where do we get this, how do we do something to the mass over here. But for now, you should think of this as something that cannot be easily tapped into. Okay, so this idea comes from Albert Einstein, the idea of mass and energy being something that are equivalent to each other. So we call it as mass energy equivalence. The actual equation is much more complicated than E is equals to mc squared, especially if your particle is moving at near the speed of light. Okay, but when they are not moving, the amount of energy that they have is E equals mc squared. So this equation is very interesting because it relates something in the unit of joule, in the unit of energy. We are able to relate to something that is in the unit of kg, which is mass. And these two things, we seldom really think of them as being something that associate to each other until this equation comes into place. Okay, this equation is like groundbreaking because they're saying that mass, right, which is something that we consider to be so, it's just there, mass, it's just there, but we are saying that this mass here is equivalent to energy, which is something that we've always tried very hard to extract, try very hard to produce more energy, but it is there in every single object. It is just there, the energy, but we are not able to tap into it. So this equation is really interesting over here. Okay, so I'm going to paraphrase the idea that Albert Einstein gave. Okay, I'm really putting it into very simple words, so you should never say that this is what being said exactly by Albert Einstein. This is just what I say to simplify the picture of mass energy equivalence. Okay, so mass and energy, they are just the same thing. Okay, Albert Einstein never really said that. I think this is me, but you can think of it like this. Okay, you should think of mass and energy to be something that are equivalent to each other. They are just the same thing, just being manifested in different form. Okay, mass is something quite physical, quite concrete, you can feel it. Energy is something more abstract, but they are actually the same thing, just manifest in different form. Okay, so if you want to release an energy, well, you just lose a bit of mass. If you remove a bit of mass, you can convert that mass into energy, then you release energy. But what you need to sacrifice? You need to sacrifice a bit of mass up. So by losing a bit of mass, you can release the energy from the mass that you liberated. Okay, but if you want to gain a bit of mass, you can actually do it. You can gain mass by taking energy and convert it into mass. Then that causes you to have a gain in mass. Okay, so we are now proposing an idea that mass doesn't really necessarily have to be conserved. If you are able to convert the energy into mass, you have an increase in mass. If you are able to take the mass and convert it into energy, you undergo a reduce in mass, but in return you get energy released to the surrounding. Okay, so this is the kind of theory that we are going to dive into for now. Okay, so applying this idea in the formation and the breaking out of nucleus, we can say that if we want to form a nucleus, we are going to take constituent particles, which are protons and neutrons. Protons represented, how many protons is represented by the proton number, how many neutrons is represented by the neutron number. So together they form A, the mass number, or the nucleon number. So that's how many protons and neutrons that we have, A, and we are going to put them very close to each other to form a nucleus. And you should expect that during that process, you will also couple with some amount of energy being released. Okay, so when a nucleus is formed from separated nucleons, energy is released. So this is what we discussed in the previous video. We talk about it being similar to water molecules changing from liquid phase to solid phase. So if you go from liquid phase to solid phase, the distance decreases, energy is being released. So energy is a product over here. That's why it's on the right hand side of the equal sign over here. Okay, but if you study the process in reverse, where you break up a nucleus into constituent particles, you should expect that the process of breaking up require you to apply some amount of energy into it. So you are going to use some amount of energy. So when the nucleus is broken up into separated nucleons, energy is taken in. So just by having a nucleus, you cannot break it up immediately to constituent particles. You need additional amount of energy being used by the nucleus, taking from the surrounding. You take in this energy from the surrounding to break the nucleus into constituent particles. So again, there's two perspectives of analyzing it, from the formation of nucleus perspective or the breaking out of nucleus perspective. Okay, but now let's try to focus on the mass. Let's try to apply the mass energy equivalence over here. Okay, so if a system lose energy to the environment, we have a loss in mass of the system. So this is similar to what we discussed earlier when we talk about mass energy equivalence. We lose energy to the environment, right? So some energy is being liberated to the environment. It's now from the system, the energy gets into the environment. So that actually means by the rest mass energy of what we have here decrease. So the rest mass energy decrease means by we actually lose a bit of mass. Okay, we lose a bit of mass over here. Only we are able to change that mass into energy, and the energy is released to the environment. Okay, again, the process of changing it from constituent particles to nucleus actually will result in the mass to be decreased. So you should expect that the nucleus to be lighter compared to the constituent particles. So there's a bit of mass disappear, right? It is not exactly disappear, but that mass is being converted into energy, and that's why that energy is being able to release to the environment, and the energy released to the environment is what we call as binding energy. Okay, on the opposite side of things, if you are taking in energy from the environment, it causes you to have a gain in mass of the system. So from the environment, you are collecting some amount of energy over here to put into the process to break up the nucleus into constituent particles, right? So because you are adding in energy into your system, that energy here will be converted into mass, and that causes your nucleus to receive an additional amount of mass. Then they break up into constituent particles. So we will expect that the constituent particles has a greater mass compared to the nucleus. The nucleus is lighter, the constituent particles are more massive. Okay, so you should expect that these two, even though they are the same number of protons, they are the same number of neutrons, the mass of them will be different. If you count here, there will be 1, 2, 3, 4, 5, 6 protons. For the neutrons, it's also 1, 2, 3, 4, 5, 6 protons. For the neutrons, there's 1, 2, 3, 4, 5, 6. For the neutrons here, there's also 1, 2, 3, 4, 5, 6. The number of protons are the same. The number of neutrons are the same. So from a logical perspective, logical thinking, you should expect that the mass are the same. But now I'm telling you that no, the mass are not the same. In fact, if you break them apart, they should have greater mass right now. But when they are closer, when they are stick together, they should have less mass. Why? Because of the process of you inputting energy into the system when you are breaking them apart, or when you release energy to the environment when you are forming a nucleus. So that process of adding in energy or releasing energy result in the change of mass, either in a gain of mass or a loss of mass of the system. Okay, so you're applying the idea of mass energy equivalence to understand that the energy release actually causes loss in mass of system, or the energy received or the energy used result in the gain in mass of the system. So one thing to take away is that constituent particles are more massive compared to the nucleus. Okay, so sum of mass of separated nucleons means by if you take the mass of 6 protons, add up with the mass of 6 neutrons, the mass here should be more massive than the nucleus itself. Okay, again, you should break away from your intuitive thinking, saying that they are the same amount of things. Why are they different in mass? Well, they are different in mass. Okay, this is what scientists have discovered. They are different in mass. Okay, in fact, if you are separated, you have more mass. If you are formed together into a nucleus, you have less mass. Okay, so this difference in mass over here, if you take the separated nucleons, which is more massive, minus by the mass of nucleus, which is less massive, the difference in this mass over here is what we call as the mass defect. Okay, defect is something that we usually have a negative connotation, means by it's something that disappear, right? Or it's something that's not good. Or in this case, the mass that is disappear is the mass that you can find by taking the separated nuclear mass minus the nucleus mass. Then you're able to get this value, mass defect. Okay, so this mass defect here, you should suspect that this mass defect here should be related to binding energy, because that is the gain of mass, or that is the loss of mass that we are talking about over here. So since we know that they are related to the energy that we release or the energy that we take in, so you know that this mass defect here should be related to the binding energy. Okay, so in fact, because we learned about mass energy equivalence, you should suspect that this mass defect is related to the binding energy through this equation, where the binding energy is equals to the mass defects multiplied by c squared. Because that's a change in mass that is experienced, right? This change in mass is converted to energy. So how do you convert it to energy? By multiplying it with c squared. Then you get the binding energy. So this is the idea. This is how we obtain the binding energy. Okay, but in the next video, we are going to talk about how do we obtain this mass defect here in terms of a proper equation, so we are able to really calculate what is the binding energy. Right now, by concept, we know that it's mass defect multiplied by c squared, but how do we obtain this mass defect? And from the mass defect, how do we calculate the binding energy? We will leave that to the next video.